Quantum computing research is booming, especially here in Vancouver, with big companies like D-Wave and 1QBit. This, along with increased representation within computing, are the main drivers for OptiQit. Our project deliverables are to build an educational kit to demonstrate principles of quantum computing to high school students, pair it with an app or website to display experimental results, and for the kit to be portable, light, and extendable.
OptiQit currently has 2 experiments. In the first experiment, the light will pass through a double slit and then be directly projected onto a screen to be viewed with the human eye. In the second experiment, we want to have less light going through, such that we can quantify it. It will first go through an attenuator to reduce the amount of light to become photon-like behavior, and then it will pass through the double slit. A linear actuator will position a single photon detector at multiple positions along a horizontal axis. The readings at each position will be reported to a microcontroller, and this data will then be presented on digital data plots. We additionally designed a signal processing circuit to optimize the amount of data that is collected. The 2-volt output from the single photon detector will go through a logic converter to be boosted up to 3.3 volts, as binary counters work better at higher voltages. This reading will then be passed to the microcontroller and then translated back into a digital value. This is the state machine for OptiQit. OptiQit begins when the user presses the red button to turn it on. The user can press the blue button at any time to turn OptiQit off. OptiQit will automatically initialize and report that it's waiting for a Bluetooth connection. Once the user connects, OptiQit will report that it's ready to start an experiment. After the user presses start or presses the yellow button, OptiQit will begin the experiment. Once it's done, OptiQit will report that it's done the experiment, at which point the user can view the results on the web app. The user can then either press reset or press the yellow button to return to the ready to start state and press start to start another experiment.
Next, I will provide a system overview of all the physical components and explain how they integrate with each other. Starting with the housing, we can see the construction that holds all the components in the kit. These walls divide the kit into 2 main sections, one to hold electronics and one to perform experiments and hold optical components. The foot-long optical breadboard takes up most of the space in the experiment section. The laser is mounted at the very end to maximize the clarity of the double slit interference pattern that appears on the opposite side. Wiring from the laser is connected to its power supply in the electronics section. This middle area is where optical components are inserted in order to complete the experiments. The linear actuator at the far end positions the optical cable along this axis. The optical cable sends the signal into the single photon detector and then the microcontroller for signal processing. The motor driver here helps interface the actuator's motor with the circuit and the microcontroller for actuator control. The electronics and circuit are built on the breadboard here. From the microcontroller, data is sent to the web app for visualization and education. Power supplies for all the electronic components tie into a multi-port power bar here. In order to minimize light entering the box, this power bar is the only housing penetration to the exterior.
In this section, we will highlight a few key models and simulations.
This is the voltage comparator circuit. Given a reference voltage, which is slightly larger than 0, any input voltage which is larger than the reference will be passed through and amplified. Here, a positive and negative output is produced. In this case, we are only interested in the positive output. This is a simulation. Given a 2-volt pulse from the single photon detector, the voltage comparator will produce a larger voltage.
The 2 most important physical calculations to OptiQit were for double slit sizing and actuator selection. The equations shown here were used for double slit sizing. We used the parameters capital D as the maximum box length and Y minimum as the minimum fringe spacing to determine the output lowercase d. This lowercase d represents the distance between the 2 slits in the double slit. With these parameters, we were able to size both the double slit and the box size. For the actuator, we used the step angle and the screw pitch of the actuator to determine the step size. The step size of 25 micrometers was sufficient to meet the required distance between the fringes, which we set as 0.5 millimeters.
In this section, we will outline a few milestone experiments conducted in developing OptiQit.
The first experiment that the team completed was the double slit experiment. The goal of this experiment was to test various fabrication methods of the double slit to produce a clear pattern compatible with an actuator. A clear pattern would happen if the constructive fringes have a separation of approximately 0.5 millimeters, as we mentioned in the calculations section. If the fringes were too close, the kit would fail, since students wouldn't be able to understand the concept of the constructive interference patterns. The results are shown here. Paper double slits were too flimsy and difficult to work with consistently. Cardstock was difficult to cut for the small gap widths. Printing double slits on acetate plastic sheets didn't work because the black ink was too transparent, even for our Class 2 laser. Layers of electrical tape with slits carved out, which we ended up using here, was sufficient for testing and experiments. We concluded 3D printing should eventually be used in the final product, which will be discussed in additional work. The second experiment the team completed, also in the optics labs, was the visible light experiment. The primary goal of this experiment was to set up the electronics required to process a light signal. We used different positioning elements like this stage, shown in the picture, to align the light to the sensor. We then compared signals of ambient light, laser light, and no light. The results for this experiment were that we were able to display light signal readings on the oscilloscope and distinguish between the signals of no light, shown here, and higher intensity laser light, here. The information from these results will be useful for signal processing. later. The next experiment used attenuation to evaluate how the intensity of light would affect the signal output of the sensors. At this point, we had not yet used the expensive single photon detector. The goal of this experiment was to vary the intensity of light to see how it would influence the inputs to the sensor. Attenuators of various sizes were used to gradually reduce the intensity of light from 100% to 0. We observed a hole diameter threshold of 25 microns, below which light passing through could no longer be seen. This indicated low photon behavior, which is still above no light, the same signal we were hoping to simulate. The oscilloscope showed a low-strength signal, and we now knew the approximate magnitude of signal that would have to be processed and amplified. It would also gather that attenuators made of slides would be more effective and reduce the light bending associated with the pinhole attenuators. The goal of this experiment was to integrate the single photon detector with the existing setup. Low light intensity is used with the single photon detector, but part selection was performed so that it could also handle the full intensity of the laser without being damaged. Procedures included properly handling, cleaning, and protecting the fiber optic cable tips, and being careful about the power output to the detector, with 2 stages of lockout to power. We were able to connect to the detector and send signals to the microcontroller to be displayed there instead of on the oscilloscope. The next step is combining all of this with the double slit. The double slit was then integrated to see if light and dark fringes can be detected in low photon settings. Procedures were the same as the previous experiment, but with the double slit here aligned to the attenuated laser. By moving the detector along an axis, areas of high and low intensity were observed by the detector, even though the pattern was undetectable by the human eye.
Now let's examine the signal processing circuit. In this example, our input is a 1 kilohertz signal with approximately 3.3 volts. We use a voltage comparator to boost up the voltage because the binary counter works better at higher voltages. The first bit is 500 hertz, which is half of the input frequency. The second bit is 250 hertz. The third bit is 125 hertz, and the fourth bit is 62.5 hertz. So we see that the signal processing circuit is working.
We were able to bring a 12-year-old student in order to test our design. We showcased our experiment and were able to discuss basic theory behind the results. It was reported that it was an overall positive and easy to understand learning experience. However, we do acknowledge this was a small sample case. Over the course of the year, we received feedback with friends and classmates to better our project into presentation and clarity.
Hello, I'll be showcasing what we managed to develop from the design my colleagues discussed earlier. I'll be walking you through some of the components you see here, and then take you through an ideal operation of this educational kit. The first component to discuss here is the laser. It is integral for all optical experiments to be conducted using OptiQit. Moving to the left here, we see an attenuator. We fabricated this by evaporating aluminum onto a microscope slide. It is moved in line with the laser when single photon-like behavior is desired. This attenuator is able to filter approximately 99% of light. Next, we have the double-slit filter, used to demonstrate the wave nature of light. Further left, we see the linear stage, used to change the position of the input to the single photon detector. And of course, this is the driver to drive the linear stage, and this is the microcontroller. The power source for the laser is located here.
For the first experiment, we move to the web app and select the double slit experiment. The introduction section seen here describes what the motivation behind this experiment is, which in this case is to demonstrate the wave nature of light and highlight a very unintuitive interference pattern. The next section asks the students to spend some time thinking about what they think will happen when the experiment we described in the introduction is actually carried out. We follow this by showing them a few instructions to set up OptiQit to actually perform this experiment. We'll now go over to the actual kit to show how this is done.
Here we see that OptiQit is plugged into a wall outlet and the laser is on. Next, we move the attenuator out of the way of the laser as seen here. Now we can observe what is seen on the observation wall.
It doesn't show up very well on video, but areas of darkness and areas of brightness should be visible. We head back to the app to see the explanation, toggled by this button over here. We can now go to the next experiment by clicking here or navigating from the home menu. In this experiment, we perform the same experiment as before, but this time with light as a particle instead of a wave. We are going to see if constructive and destructive interference is still visible when only a single photon at a time passes through the double slit. This time, however, since a single photon is far too little light for the human eye to see, we will use a single photon detector and sweep it along an axis to observe areas of high concentration and areas of low concentration. All the sections that existed in the previous experiment can be seen here. We now go to OptiQit again to see the experiment in action.
We once again ensure OptiQit is plugged into a wall outlet and the laser is on. This time, however, we move the attenuator in line with the laser.
Now we go back to the web app to connect and pair with OptiQit. To best illustrate the results of this experiment, we have shown OptiQit along with the live updating graph on the web app simultaneously. You'll notice that as the linear stage is moving, the graph seen on the web app is slowly updating as well. It is fascinating to see that despite sending in only one photon, the same interference pattern is still observed. We now go back to the web app to see some explanation. This duality of light that we have just illustrated in these two experiments is the basis for all optical quantum computing. In this section, we discuss some real-time operating system features we weren't able to incorporate into our main kit.
Here we'll demo OptiQit with a real-time operating system, which means we're running multiple processes in order to be able to do several tasks in parallel. First, let's turn OptiQit on. The indicator LED is blue, and it says waiting for Bluetooth. Let's connect. Alright, we're connected. The indicator LED is green, and it says kit ready, press start. We can either press the blue start button, or we can press start remotely. The LED is red because there's no signal. It gives a higher pitch when there are more readings. OptiQit gives a jingle when it's done. Now we can either press reset to do another measurement. See, we can start a new experiment, or we can turn OptiQit off. The experiments can be viewed in a graph on the web app.
Due to circumstances at the end of the semester, closed facilities have prevented some of OptiQit's components from becoming fully complete. Additional work that was restricted including the kit aesthetics and manufacturing of existing prototypes. The plan was to 3D print final models of these brightly colored parts using the IGEN 3D printer. The green slider base shown here would provide an effective and secure method to fix the double slit and attenuator components to the optical breadboard. These holes are dimensioned for the M6 screw size used commonly in optical breadboards. These modular parts can be used in both our kit and further development in an optics lab. The blue rod shown here is an axle that connects to the slider base with a tight interference fit. It ensures the optical components are aligned with the slider base. The rod also interfaces with this pink part holder, which better anchors the double slit and attenuator compared to our current setup. The pink part holder slides along the rod to switch between experiments. Most importantly, these 3D printed components would provide an interesting interactive element for the end users of the kit. Brightly colored parts would make the instructions easy to follow and assemble as they stand out from others. We also would have manufactured a final version of our double slit prototype to use in the end product. The current double slit is functional but subject to deformation. The final double slit would be more rigid and would fit in the slider base for reproducible alignment and precision, something that has challenged us during testing. Other work cut short this year was polishing the aesthetics and final visual aspects. The exterior housing would have been painted and branded, and the interior surfaces would be blacked out to reduce reflection. The final step to finish the lid interface is lining the edges with foam to block ambient light from entering.
As part of the Diversifying Talent Consortium, the project has longer-term goals such as to mass produce the OptiQit for provincial and national education throughout many educational settings. However, our team has also came up with some short-term goals if we would like to work on this project outside of IGEN, such as we would like to include additional experiments, like the original beam split experiments, to prove that light can act like a single photon. Another goal is to generate lesson plans and teaming up with Gearing Up or other educational camps to demonstrate our project in person. Also, we would like to offer our website in multiple languages.
We'd like to extend special thanks to everyone who supported us throughout this project.